Dear academicians, dear students, dear all faculty members, this evening we are continuing to our Archidesign Timber Talks series for fall semester season with a valuable guest from Spain, but he is in Italy now, in Rome. We will focus on restoration and conservation of timber heritage, and I will try to moderate this meeting. Please ask your questions and at the end of Mikel's presentation. I would like to introduce Mikel Landa briefly for our participants. He born in 1965 in Aloria, Basque Country. He finished his master in architecture in 1991 in the University of Navarra with a doctorate in 1997 and an Extraordinary Doctorate Award granted in 1999 by the same university. For 25 years has been devoting part of his activity to teaching in the University of Navarra and other national and international universities. He has developed his professional activity in his own office since 1991. In 2000, he created, together with Alonso Ocandiano, the company Landa Ocandiano Arquitectos, that works mainly in the heritage conservation. As a result of this collaboration, they have performed a number of investigations in heritage. The diversity of works includes master plans, strategic plans, intervention in heritage and cultural landscape. Survey interventions in wooden heritage are his specialty. The most remarkable project remains the integral recovery of Anana Salt Valley cultural landscape. His participation included leading the master plan, negotiations with stakeholders, fundraisings, the creation of foundation, and management of the sites. Today, Mikel Landa is the president of advisory committee of ICOMOS and has recently been president of International Wood Committee and vice president of the Spanish National Committee. The word is yours, Mikel.
Okay, thank you so much, Demet, and thank you for inviting, and a pleasure to be here with you. Well, I will speak. I will share the presentation with, I don't know if Demet, you have to activate my capacity of sharing.
Okay. Salih Hocam will support us.
Okay, that's it. So now I share and screen. So let me know if you see it.
Yes, that's perfect.
Yes.
We are seeing
perfect. So so today I will speak a bit about heritage, wooden heritage conservation mainly, and from the focus of minimal intervention. What minimal intervention is in certain situations, because this is a concept that it's different in each, or I mean how it is focused is different in each one of the cases, regardless whether it's wooden heritage or any other kind of heritage. So, see, obviously you all know what the Venice Charter is. I won't speak about the Venice Charter today, but just to set as a beginning, which is a document that was created mainly thinking in the kind of heritage that we understand as such in the south of Europe, which is, well, you're seeing the it needs interpretation when applied to wooden buildings. It was not thought for wooden buildings. So in 1994, Knut Einar Larsen, who's an architect from Norway, and he did a work in Japan, and he studied hundreds of buildings and the conservation of those buildings, and did a wonderful book. It's a small book, but it's It's titled Architectural Preservation in Japan. And in that book, there's a question which is very relevant to this, which is, do historic buildings made of wood behave differently from buildings made of more durable materials, so that the internationally accepted preservation doctrine is less relevant? And when he speaks about the accepted preservation doctrine, he's thinking of the Venice Charter. And this is the basis of it's on the beginning of the book, and then he explains what the Japanese understand on heritage or wooden heritage conservation, because most of the heritage is wooden. So starting with this question, we go to wood, which is the basis of this of the question and the basis of the reason of doing that 1999 document on NARA document on authenticity, which is a base for many conservation works and strategies. Okay, this is wood, and wood serves for instance, for this. You can see probably the simplest and most efficient, even for CO2 and climate change, a structure you can imagine. It's just a tree that has been cut and let fell from a side of the river to the other side of the river, and it's a bridge. It's a simple bridge. It's not the most comfortable bridge of the world that we can see, but it's a bridge, and it works as a bridge, and it's made of a material which is wood, and the image can tell us a number of the properties of wood. One is the ease on how we work with it. Second one would be that it's a good material for be used as a structure. It works well bending, so it's good for a beam, which is what we're seeing. It's a beam, so it works well in compression, tension, bending. So it makes a very suitable material for building, and it's been used all over the world from the very beginning until today for building not only houses but also ships and so many things. So we need to know that the wood is a material which is different to others in a series of concepts, such as hygroscopicity, which is the property of wood of getting moisture from the air which is around, or the contrary, to let that moisture to give it to the air around, depending on the humidity, on the temperature of the place in which that wood is. So it doesn't behave as metal, it doesn't behave as concrete, it doesn't behave as stone. It has its own properties. Another one is anisotropy. Its properties are different in the three axes in which we can organize any cut, any of the wood, longitudinal, radial, and tangential. But we also know that the properties are different, and that's the reason why when it shrinks, because it's getting dry, it cracks. And it always cracks in radial direction because the tension is double in tangential than in radial. That's one of the consequences of its anisotropy. So we see the cracks, we see them, they are radial, they are there, and they're not a problem. We just need to know when they can be, and most of the time they're not a structural issue. We can see them there in this wooden post. There's a big crack, and there are many small ones. And even on that a horizontal element, we can see those small cracks. They're not a structural problem, but we know why they exist, why they happen. There is another one is natural variability, and natural variability is due to many things. One of them is the species of wood. There are thousands of species of wood, of commercial species of wood, and each one has different properties. So that anisotropy is different. The shrinkage and the coefficient is different in each species, but also where you see those elements, those horizontal elements which have been drawn here, those are branches. Branches means discontinuity of wood. So if we take a plank out of this trunk, we see it on the right side, you can see that we cut those branches, which are always radial, and they involve a discontinuity in the grain of wood. So they involve they reduce the structural properties of that element. The bigger the knot is, the lesser the structural properties of this wood are. So, well, and then there's the question of durability, which was on the question we showed before of Knut Einar Larsen. He spoke about more durable materials. So he assumes that wood is not a durable material, and we can see here that a wooden element that has been almost completely destroyed by moisture and the action of fungi. So yeah, there's an issue with durability, but to say that wood is not durable is not as simple as that. We can see a metallic beam which has been not completely, but is on the way of being destroyed by corrosion due to moisture also. So moisture is an issue also for metal, and you can get to this extreme where the beams, metallic beams, in 100 years of use, they've been completely destroyed because of moisture, which makes that, for instance, the French, they need to do constant maintenance of the Tour Eiffel in Paris, because if not, it would have the problems we've seen in the former images. So it needs maintenance, and they do it, and that's why the Tour Eiffel is still there and will still be there for many, many years. And what we can see in this image is one concrete pillar with the steel elements inside that have been corroded, and their dimension, they've grown in dimension, and they've cracked. They made cracks in the concrete, so that the concrete element itself, the pillar, is not it has lost resistance. And what we see around is wood. So the non-durable material is more durable than what we think, or what we call durable material. So it's kind of a contradiction. This is a restoration works we did in 2016 very close to Bilbao, in the coast, in a very industrial and coastal and exposed the situation in which the owner told the carpenter, probably he told him, okay, because it was someone, an industrial man with a lot of money, he told probably the carpenter, put me the best wood you can here. And it was teak. Teak is a wood which is very stable, and it's a wood that is not damaged by fungi or termites or any kind of. So what you see is a grey wood, because it hasn't been maintained since the Spanish Civil War, but it's still there and it's in perfect condition. So this is before the restoration, not after. But we also know that there are buildings such as the Urnes Stavkirke in Norway that was built in the 12th century and still standing. Obviously, they maintain it. They care for the building. They've been caring for the building for so long. So that's the reason why it's still standing. So durability is linked to maintenance and to the care of the people that is managing, using the building. And the case of the Horyuji in Japan, which is a 5-story pagoda in the old capital of Japan, which was Nara. It was built in 670, which is well, a long while ago, and it's still standing. this building and the former one in Urnes are World Heritage, both of them. Impregnability. This is a very relevant property of wood when speaking of heritage, because we need sometimes, from time to time, we need to protect wood, and we protect it with chemicals, and that chemicals, they need to get into the wood. So if the wood is not impregnable, you cannot protect it with chemicals. If it's impregnable, then you can protect it. This concept of impregnability is very related with durability. If you have as the image we saw before, the teak, which is a very durable wood, it doesn't matter whether it's impregnable or not, because you won't treat it. It makes no sense treating it. But if you have pine, some kind of pine, then you need it to be impregnable so that you can protect it if the use will be outside or in any place where moisture can access to the piece of wood. So how do we build wooden buildings? We need two things for that. One of them is the wooden members or wooden elements, and the second one is the way we join them. And I will be very short, but we can use knots, and knots can be this in Ethiopia, in the Afar region, or this one in Galicia in Spain, but also in Japan and in many other places. The roof of this building in Piornedo in Galicia is tied with knots. Nails are simple elements that have developed into screws, into a metallic complex fasteners and joinery that serves for so many purposes. But a nail can do such a simple thing as this one. This is also in the Afar region in Ethiopia, with a wooden pillars and nails with only one nail, and you get a building. It's not very structurally efficient, but it works. So if that's what you need, then you get it. And here you have a more complex vaults made of planks and counter planks that are nailed to one another, and you can see the nails and the limits of the planks, because you always get a plank from a tree, and a tree is usually straight, so you cannot do the complete arc with a single element. You need different elements. So this double arch system that was used for centuries is quite an efficient one and interesting one, and you can see it in the Cathedral of Lima and other buildings in Europe and in South America. Another way of joining is joinery. Is the traditional joinery. That would be the third one. We've spoken about knots, about nails, and this is joinery. This is the most typical, or the one most recognizable for wood, which can be as simple as a simple support with this joist just put in top of the beam, and that's it. It's as simple as that, or a half joint, or then. But with those two joints, you can make this building, except the roof. All the rest is made with all those simple ways of joining. This is a typical facade, stone facade in the center of any Spanish city, but it can be also Italian or French or from so many places. And inside of it, everything's wooden: the pillars, the beams, the joists, and the roofs. So we go forward. Sometimes you get the structure in the facade as a structural and also decorative element, as in Bayonne in the Basque Country in the north in France, or you go to Tibet or close to Tibet in Yunnan with those Tibetan temples, which are made with the same principle, with very, very simple supports or half joints, and then you have the building made in. But the image is quite different, but the structural concept is the same. Joggle joint. When you get an angle and you can have a truss like this one, in which when putting one and a few meters later the other, and then the other, you can make a roof. And a roof that it works quite well because it only transmits vertical efforts to the walls, to the stone walls. So structure is quite interesting. This is a medieval tower in the north of Navarra, built in the 15th century, restored in 2002 by a teacher of mine in the university, Maite, and she did an extraordinary job in restoring this. But the building is an extraordinary example of how to use wooden joinery. What for is each kind of joints for? And they've been used with a very precise idea of what they needed as a structural function for every element. So this is the structure, 2 stories made of stone with the inside made of wood, and the 2 upper stories are completely made of wood. And this is because it's a consequence of a war which was lost, and then the winner, which was Spain, said, okay, you will cut all your towers, and the upper part of it will be made of wood, and this is a consequence. So the consequence of a war gives us centuries after an amazing heritage, and this is it, seen from outside. The fourth way of joining wooden elements, it's glue joints. This is quite newer than the rest, but you can see the chair with all those finger jointed joints, and it has a capacity of supporting moments. So you can take this pillar, which should be on the back side of the seat. You can take it out because it works without, and that's quite innovative in wooden construction in general, and that gives a way for different products which are on some of them. This one is not that new because glulam, we've been using it for 100 years, but with small elements you make big beams, and then with those big beams you can do amazing structures that you can that you obviously can't think on. Many of them you've seen or you've loved. A LVL, laminated veneer timber, which is a kind of a very thin layered glulam, which is structurally more efficient and uses wood in a better way, or a CLT, cross-laminated timber, with which you can do big constructions, and it's used for many purposes today. It's very popular, at least in Spain, but in many other countries also. But imagine, you all know this chair that Alvar Aalto did, not 100, but 90 years ago, which is quite a lot. And it also was quite innovative at the time, but it's the properties of wood with glue what makes this chair be possible. And that's it. And I would say it's comfortable. But it also gives us the opportunity, together with those CNC milling machines, to do those amazing structures like this one. We did that a few years ago in Añana, in the Salt Valley of Añana, and it's an ellipsoid made of glulam, and this is the shape of it. So it gives so many possibilities that in new construction, but also when speaking about conservation, what we're doing today, the techniques, the way of focusing how to work with wood, it's specific to the material, specific to the culture, specific to the building you have on face when you have to restore something. So wooden heritage, it gives what we've seen, gives the possibility of doing so many different buildings, so many different structures, that the heritage itself is very diverse, and the conservation processes are also diverse. And we go forward. This is Añana Salt Valley, just an image of a wooden heritage place in which to make salt, which has been working for more than 6,000 years now, and it's been restored, and it's working still today. I mean, it hasn't been completely abandoned at any time, and it needs a very specific approach. But I would say the same with this is a small church in the Basque Country, close to the place where I live. Or this one, a very, very small Gothic vault in a very tiny hermitage in the forest. Or this one, but also in Turkey, you have beautiful examples of wooden heritage, and so many of them. But we can go to Slovakia, to Ronsek, which is also World Heritage, or to this one, Surdesti in Maramureș in Romania, which is also World Heritage, made of oak 250 years ago, with 57 meters high, which is a lot. Imagine 57 meters in wooden construction, and the scale of this is simply amazing. Or the Kisi-Pogost church in Karelia, Russia, and that amazing shape with those domes on the top of it, 21 of them in the main building, which is the winter church, and the summer church has a few of them, but it's also another amazing structure made of logs put horizontally and then crossed in the corners one another, making a quite simple but amazing construction. And then we go to Asia, and you can imagine all those complex structures made of wood, and with complex. Not only the structure, but the joinery is amazing. It's complex, and the result is very different architecture to the one we can see in Europe or in the closer Asia. So how do we intervene in those kinds of buildings? Is there a unique method? Well, we have to know that this is about science. I mean, it's not about having a good idea and then just following it. It's about science. It's about analyzing. It's about having a method. So if we're prepared then we will do it well. And for that, we need criteria. I mean, we need a methodology, and we need techniques, and we need all three of them. It's not just to have the criteria very well in mind, and then we forget the methodology and we cannot master the techniques. Or the contrary, we are very good in techniques, but we don't apply a good methodology, or we have no idea what criteria. We need all three of them. So good criteria, correct methodology, and then the appropriate techniques. So we will speak mainly of methodology and techniques. A methodology, I would say it all begins with research, with different kinds of research, and obviously there's historic research. It can be archaeological research. There can be many kinds of research, but I will speak only for a few of them. Geometry is very important to know how the building is, and for that there are different techniques. One of them is to go there and to measure it by hand and drawing by hand, and then going to the office and drawing in AutoCAD. But that doesn't give much accuracy to if the building is a bit complex. So in this case, in 1998, the Cathedral of Victoria, of Santa Maria, during the master plan, this was done with pairs of photographs, which is called photogrammetry, and then all the stones, woods, and corners of the building were drawn on computer with accuracy. It takes time, but it depending on the building, it's worth it. But we'd use this for another amazing project we're actually doing in located in the Basque Coast, which is a shipyard, and which is completely deformed in every direction. So you cannot Well, you can, yes, but it's difficult to do it in the traditional way. So what we did is a laser scan, and with a point cloud in the computer, then we draw it piece by piece, element by element, each one of them in the exact position, dimension, and in relation with the others it has in reality. But you can also use BIM, I mean Revit or any other kind of software that works in BIM, which is the one we use here for the Avaroa Palace, which is also in the Basque coast. This is it. This is a view from the outside of the building, and then with the proposal for new buildings, also made of wood. Obviously, you need a diagnosis of what the condition of the wood in the building is, and for that you can track the different every data that is relevant for the wooden structure. It can be also the cracks and following the how the cracks are evolving, whether they are evolving or not, and at which speed they are evolving, and in which parts of the building they are still, they are not moving, or in which of them they are moving. So that's quite relevant to know if the building is still sagging or leaning or whatever. Measuring the moisture content of wood to know whether the wood in the upper one is 12%, in the lower one is more than 44%. So it could be, those are samples in the office, obviously, but if those on the side would mean that the one on the upper side of the image is correct in terms of moisture, and the one below has a problem. And yeah, that gives information that can be relevant, but also some I would say more modern auscultation techniques like the resistograph, which is like it's not like it's a drill. It's a very thin drill that gets into the wood, so it's not completely innocuous. It makes a very small hole in the wood, but sometimes you need that hole to realize whether there's an issue, whether there's a structural problem or not inside the wood. It gives a lot of information, and that information, all that information of any kind of method that you're using, any kind of different measurement you're doing, you can put it into a drawing and then display it in a way that it can be understood as quickly as well. This is an image of the master plan of the Cathedral of Santa Maria in Vitoria, in which element by element of the roofs, of different levels of the roofs, were analyzed. Moisture content, biological pathologies made of termites or fungi or whatever, and also construction, structural issues, and then even you can go further and give a kind of qualification, of structural qualification, whether each one of the elements is still appropriate for structural use or not. And then after all that information, you can decide in a better way than without that information, and we go forward. So techniques, there are many, but I usually like to concentrate on those that carpenters have been using for centuries. You know that a wooden structure is usually more isostatic than it's not like a concrete structure in which you have a rigid joints. This is about for having this upper left structure working, you need to put a diagonal on it so that it doesn't deform. The Japanese and the Asians, they do it by repetition of elements, vertical, horizontal elements with knots that are much more sophisticated than ours. That's why I drawn them with a square instead of a circle. Those Japanese knots, some of them obviously, they have a certain capacity of absorbing moments, flector moments. So that makes them, if you repeat it in a certain number, then you have a approximately rigid structure, which is fantastic for earthquakes. They work well with earthquakes. But also, I wanted to I go backwards to this one. The fact of being isostatic means that if you intervene in one part of an element or on an element, then you're able to control the whole building. If you are able to repair one single element, in any case, whether it is bending or compression or tension or whatever, then you're able to restore the whole building. So the approach is global, obviously, but the intervention can be local. You can restore, repair, reinforce, or whatever you have to do to one single element, and you're doing something which is appropriate for the building. And this is the kind of repair that the carpenters have been using for centuries in so many countries, which is a graft. We could call a graft a repair or reinforcement carried out in a wooden structural element by the only use of wood and joining both parts. When I say both parts, I mean the element you're repairing and the element, the new one that you are giving for the repair. So joining both parts with joinery, fasteners, glue, or a combination of them. So here you can see in Drohobych in Ukraine the replacement of one element here on the base of the structure of the porch. So this is a simple substitution of an element by another. You sometimes also have been replaced and a few elements, but the rest this keeps being the old structure. Or this one, which is a traditional joint, a dovetail joint used for repairing the lower part of a pillar. The lower part of a pillar, instead of replacing the whole pillar. This is in Japan, in Sürücü Temple in Takaoka, and in which the place where the pillar is in contact with the stone, and due to the rain, due to the moisture, it gets damaged by fungi, and this is a repair made by a carpenter, and you keep the most of the pillar there. This is also in Japan, in Tokyo, in the garden of Tokyo, and you can see some elements that have been replaced, some elements that have been kept old as they were in the place they were, and some have been repaired as this one. And you can see the new part of the element that has been joined to the old part of the same element. And the new one, you can see it's in Japanese, so I have no idea what's written there, but it's the information they want that someone in the future to know, so that they know probably the species, the year, or whatever information they want to give to the future restorers of this building. That's something they do very well, the Japanese. I think that we all should do some kind of prepare information for the future. Well, a graft in the top of a pillar which could have damage, and with a simple joint, then you can only replace a small part of the pillar, and then you have the pillar which is structurally efficient, as it was before at the beginning when it was placed in the building, or different ways of joining which are more complicated, made by, in this case, by the Japanese. So graft, structural grafts, those are a more modern, I would say, ways of joining, even if the design is simple and is traditional, because they are traditional ways of joining, but then as they are glued, the behavior is different. So then you can control the quantity, the amount of structural efficiency you recover in every element. So depending on the design, how you do it, then you can use it in different places of the same beam, because it's more efficient or less efficient. In this case, the more you go to the right, the more efficient the solution is. Sorry. and forwards. And then we can see a few examples, I think, or maybe just one, of what a graft is. This is in the Condestable Palace in Pamplona, which was restored in 2006, 2007. And I will show just one case because we have 1 hour. We've started a bit late, but I would like to keep to time. I will put this example, which is a theater in Asturias, which is in the north coast of Spain. And the building was built in the beginning of the 20th century. And it has something quite peculiar. And it's that when you get to when you see it, you see a normal theater, a normal small theater of any city in Spain. But it has something very special, which is that if you take those seats out, then you can put this surface horizontal. So you have below the seating below the seating platform, you have a wooden mechanism that helps make the movement, so you can have it inclined, so it can be used as a theater, or you can have it horizontal, and then you can use it for any purpose. Like it can be an encounter, or dancing, or an exhibition of photography, or whatever you can imagine. And you have a rotation axis, which is this one in the left, a hinge. So the issue here was that the municipality called us because there were certain pathologies, and they say, okay, can you analyze what the pathologies are and what the intervention here should be? So we saw that the pathologies were quite severe in certain places of the structure. Well, the first thing we needed to do here is to get in, see the structure, and try to understand how it worked, because it was not easy at the beginning. You see wooden pillars and wooden diagonals and wooden elements in every direction, and say, "Oh my God, how does this work?" So first is understanding, and the second one is drawing. We did this without that was made many years ago, so we didn't do any laser scan. We did it by hand. So we put a table inside this place with a laptop, and we did the measurement, the drawing, everything inside the building until it was finished. And then when it was finished, we went to the office to continue with the project itself. So the hinge is this one. The axis of rotation is the one on the right side. And then all these elements are pillars. And obviously you need two kinds of pillars. The pillars of the structure when it's in the lower position, and the pillars of the structure when it's in the upper position, which are the ones on the lower position, the ones on the upper position there. And then you need some kind of balances to make, to help the structure go up or go down. And then the mechanisms which are here and here. And this is the only metallic element, which is a metallic beam, which serves for making the structure go up or down. And on top of that, you can see a floor made of 4 beams. The beams are triple, so it's 1, 2, 3 pine beams put to, one besides the other. So we have 4 beams and joists, and many joists. So it's quite simple, but it's very thin elements, because if you have to move it, then you need it to be light. And so you cannot use big elements, big, thick, square elements. They have to be thin. They have to be quite lightweight. So the difference between this image and this other one is the position of the pillars. If you can see that on the pillar one here, P7, is in one position where the structure is up, and it's in a different position where the structure is down. So that makes that you have to calculate the structure not only once, but more than once. You have to calculate it in the position, in the lower position, with the pillars and the distances between pillars that are in that position. And then you have to calculate it again when it's in the upper position, because the distances are completely different. Some of them are completely different, and you have to make it work in both situations. But then there's another one, the third one, which is when it's moving, because when it's moving, you only have the support of one extreme, and on the other extreme, there are no pillars. The pillars are not touching the structure while it's moving. So you don't have the load, the use load, because when it's moving, you have no one on top of the structure, not even the chairs. But the distance between supports is huge. And once you did 3 calculations, then you need to do the diagnosis of it. So what we saw when we got in is that the structure was painted in red, because someone thought years ago that it would be nice to have it red, but it has no sense, no interest in having it red. What for? One of them, because it's out of vision. It's a structure which is hidden, it's not seen. The second one is that what you're doing is you're hiding, the painting is hiding the pathologies. So you don't see them. You see a nice structure, you don't see the pathologies, but we see one here on the lower right side of it, which is the beam broken. And you can see here this cantilever that is something's missing here. And then you can see that this pillar is not vertical, and it's not vertical because of the fungi on its encounter with the concrete, because it was put into the concrete, so it was completely destroyed on this place. And once it was completely destroyed, this diagonal was pushed into the left side, so it took it out of its place. So yes, there were a number of pathologies. And then you can see this pillar, which is the pillar when the structure is on the lower position. And then you can see that this pillar, which is inclined, and when the structure goes up, it gets to a vertical position with this rack, or I don't know how is it called. So you put it vertical, and then you have the structure in the upper position with this one, with this pillar, which is supporting nothing in that position. So those are some of the pathologies. This is one of the main beams of the whole structure, and the reason for the pathology is quite clear. It's because of the distance between the upper part of the pillar of the support and the lower part of it. So this is a bending moment here, and another one here, and another one there, and it's broken in 1, 2, 3, 4, 5, 6 in many places. So this one we had to replace it. There was no way of repairing a beam with so many cracks, so many pathologies, but most of the rest were respected. So the project just proposed a few. So you can see here in colors the few elements that were repaired or reinforced or whatever, and in this blue, those are sacrifice wooden elements that we will see better in the images afterwards, or the repair of the beams due to side effects, and so those are, and this element here, this is also a sacrifice wooden piece for the wheel, and you will see it now in the image. So those are repairs of the main beams, which are these, which are made of pine. They repair the graft and the beam itself, obviously, because if the beam is made of a different species of wood, then we would use a different species for the repair of the beam. And those parts are glued so that the structural efficiency is I would say, complete, total. And in this case, those joists were reinforced because there's the technical code in Spain that you have to keep. And in this kind of buildings, there's a difficulty sometimes in keeping to every aspect of those technical codes. So in this, this is an example of trying to accomplish with every detail of the code, but it's simply impossible. You cannot do everything. You have to get as close as you can, but in some cases it would mean changing the whole structure. So that's not. So what we did here is we put a limitation in the use in the surcharge of use, and that's it. That's what you can do. You see the structure here finished with those elements that recovered or reconstructed, I would say, because those are concrete new elements that were placed because none of them were remained. And this is the beam as you saw before, broken in several places. We changed it with a different species due to fire, to improve the response of this structure in case of fire. We didn't get to 100% of accomplishment of the norm, but that's the reason why we put some sprinklers that would activate in case of fire, so that the fire is finished. And the only time, this is the only time we've used products to to improve the response of wood in case of fire, but those are products that give a different color to the wood. It makes them, it separates them from the air, so the wood doesn't breathe anymore. And it only gives you 15 minutes, which sometimes 15 is enough for saving lives, but it's the only time we've used this kind of products here in tumescent products. And forwards, this is Manolo using the metallic mechanism. You need two people, Manolo and another one, to move this well, I don't know the English name for this element, which has a beam on top of it, and then it goes upwards or downwards depending on in which direction they rotate this lever. And this is the structure being moved. So you can see the pillars which were constructed for the lower position, which are separated from the beam, which is being moved. I cannot remember at this moment whether it was moving upwards or downwards, but it's moving. And this is the kind of wooden element, sacrifice element. In this case, is a hardwood with a, you can see with a screw here and another screw there to make to protect the original wood from the wheel, because moving this structure means that this wheel will go backwards and forwards, and then it will damage the original wood, and it was damaged. So we put a sacrifice wood, and if it's damaged in the future because it's been used many times, which I hope it will happen, then it's a question of changing this small piece of wood, but not needing to repair the beam itself. And this is the structure in the lower position with all the elements according to that position, and that one is the other position, which is the horizontal one with all the elements, with all the support. I think you can see here this support, which is vertical, and it's in position because the structure is up, and here you can see it inclined because it's not working. It's this one which is working, and in the other position, the one which supports the structure on the lower position, it's in the air. It doesn't work. because it doesn't need to work. It's the second one which does the job. So you have those two pillars, and it's the same case in every part of the building. And then you can see the building, the theater used for a different purpose, which is, well, this is the inauguration with all the politicians of the city and that kind of things. So this was the example I wanted to show you today. So this is it. I will try to.
Okay.
Okay.
Just finished, I think, yeah?
Yeah, I don't know if there are any questions.
Thank you very much for your presentation. I think we have some questions. I hope we have some questions from our students or academicians who can share their questions with us. Thank you very much. It's very informative, and also thank you very much for the case study, Palacio Valdez Theater. It's very interesting using timber as protecting timber, unique timber or authentic timber materials in the roof structure. Thank you very much for this. And okay. you also mentioned that timber is an organic material. We always talk about this timber is an organic material. It's an anisotropic material, and all timber species has unique behavior, unique properties. So if we want to design with timber, we need to understand the timber species. If we use timber as a solid timber, not like a glulam, CLT, or the other industrial timber materials. If we want to use timber as a solid material, like protection and conservation works or restoration works, you mentioned, we need to understand the timber species. For example, a teak example you shared with me. Teak is very durable material against the organic or biological effects like fungi and insects. So first we need to understand the timber species and the different behavior against the natural effects and also against to we need to understand their structural mechanical properties. For this, I would like to thanks for this. You also mentioned this again for us. And then you shared what is the rules of or starting point of restoration is survey. It's very important for us because we need to understand, we have to understand which or how we can protect. We clearly understand the structure first. What is unique, what is necessary, what is added later, or it is authentic or not. Or we need this elements or not. We need to understand this first. So thank you very much for summarizing all these issues for us. Thank you. Just I am trying to talk about Mikel's presentation. Maybe someone wants to ask a question. Nilay Hocam. Yes, please.
First of all, thank you very much for this very informative presentation. I think we all learned a lot. In fact, after seeing this presentation, I thought that the title was really fitting because I think during this conservation process, you are kind of also thinking about the whole lifetime of the building, not only the past, but also the future of it, especially the maintenance. I mean, even in the conservation process, I think you're also kind of thinking and calculating about the future maintenance, right? Is that an important criteria in your decision-making processes? And as I have seen, I mean, every solution is very unique. I also, question whether economic sometimes restrictions are also critical in decision-making processes.
Yes, they are. Economic issues are very relevant in heritage, and sometimes for good and sometimes for bad. Because when you have too much money, then sometimes architects are tempted to destroy heritage to do something beautiful, and sometimes it happens. So I saw it in a building in Vitoria where a beautiful project was done, but it was not the appropriate place for doing it. So every timber structure in the building was destroyed, but at the end of the works they lacked money, so one of the rooms was kept, and then we had to restore it a few years later, and it was quite unique. It's a pity that all the rest was destroyed, but that one was kept, and it was because of money. So it was destroyed because of money and then kept because of money. It's a bit contradictory, but that's it. Yes, that's it. And sometimes it's also irrelevant that in heritage, at least in our place where there's not that much money for wooden buildings or for heritage, and you need to do projects in steps. What first phase, second phase, third phase, and then 1 year you do first part of it, and the second one you do it the following year. So it gives you time to think. It gives you time to really understand whether the first idea was the good one or not. And sometimes it is, sometimes it's not, and that's a good thing. And mainly some buildings which are complex, which are different, which are unique. And when you get there the first day and say, "Oh, what can I do with this?" And what and you cannot imagine on the first sight what you were able to do, but then you have time, so you draw it, and while you're drawing it, you're thinking, and so and then you get to apply that minimal intervention concept better than if you go the first day and say, okay, this I have to take it out, and this one I have no. Probably on the second thought, you really understand that you can keep this, and then you can keep that. And thinking on the future, yes, obviously, if we are working with heritage, we're not thinking that this building will be over 50 years later. We're doing it for a long period of time. We will not be the last restorers of the building, and that's I think that's a way of thinking. So what Demet has said before about the species of wood and the relevance of the species of wood, it's one of the most delicate and relevant decisions in conservation of wood heritage, to select the appropriate species for each situation, and sometimes I could put an example of the Cathedral of Ica, in which we're working now in Peru, and there's been an issue with termites, with specific elements that have been attacked by termites. So and then there were earthquakes, and together earthquakes with termites, then there was some kind of damages in the building. So only by repairing the elements that have fallen down, and some of them you can put them again on top because it's wood. I mean, when it's falls, imagine an arch which has fallen down from the roof because of the earthquake, and you repair the beam that has failed, and then the arch, you can put it on top because it's not broken. It has suffered, but it's not broken. And the beam that has had the problem, you can replace it by another one, which can, I mean, because it's destroyed, you cannot repair it in this specific case. But if you do the same original design, changing the species of wood so that you put a wood which is more durable, then you will have 250 years later, let's hope, that it will be better because it will not be attacked by termites. And it's a simple decision, but it's a very relevant one.
Thank you very much for the elaboration.
Thank you very much for question, Leo Hocam. Is there any question from students? Do you have any question? No, there's no question. Maybe if you want, you can write your question at the chat box, and I can read your questions. No. And I also Mikel, you also mentioned that we are trying to keep intangible heritage. We already seen some writings in an example in Japan, some writings there, some numbers, maybe some material information on the new timber side of the repair work. This is a kind of intangible heritage. We are trying to keep this kind of things in our restoration works, also trying to keep workers' notes on the structure. I mean, it's not like a writing notes. It's a kind of some hand tools. Hand tools, if they used, how they used some hand tools on the structure. It gives some information about techniques also, and tools
Yes.
they used also. It's a kind of intangible heritage.
Yeah. I think intangible heritage is something that we are still trying to figure out what it is. Not what it is, but the extent of it, because it's about many things, and the one you say is a very relevant one, and it's very different how in different parts of the world it's been also taken into account. The Japanese, they're very good in so many things, and in this one also. And but it depends on, because they do have the organization and the economic capacity of doing it. So they have professionals, and even they complain as we do. They say, okay, we don't have so many professionals, but they do have professionals that we don't.
Sure.
Or we it's difficult. I mean, using the old tools sometimes is a question of money when you don't have that economic capacity of in a building, and then you cannot use that old tools. That it's something that it's difficult. It's very difficult, and it happens in most of the places. I mean, some techniques are lost. So I think that should go to a next level. Let's try and keep the and care about the carpenters, tools, about the techniques, about the ways they face every detail of wood. But there's another one which is also relevant in wooden structure, which is the structural capacity. I mean, you have a beam, and you can face the intervention in a beam in a few different ways. One of them is you keep the material and you don't touch it. So if you don't touch it, then you put a support, and that's it. That's all you've done. A very beautiful support. That would be an Italian approach. But you do nothing with the structural efficiency. So you're keeping the 100% of the material side of it, but you're losing the structural efficiency. So it's not working anymore. So if you do a repair, the kind of repair I've shown, or another one, and maybe you destroy a small part of wood because you need to do that joint, that new joint, but then you put wood to repair, and then you've destroyed the 1% of the beam, or 2, something like as few as that. But then you have the beam acting as a beam again.
Sure, absolutely. Okay. There's no question, I think. Thank you very much, Mikel, for your time, for your effort. Thank you very much for participating to us this evening. We have a little tradition here in Archidesign Timber Talks as Bahçeşehir University Faculty of Architecture and Design. We donate in our guest name. A donation has been made in your name to SAFE Foundation, of helping underprivileged children for equality in education. and I will send this document to you via email. Thank you very much for your all effort and time again.
Okay,
thank you.
Thanks to you for inviting. It's a pleasure.
Okay, have a nice evening. Thank
Same
you.
to you.
Bye bye.
Bye bye.
Bye bye.